All right, gang. So I did want to bring this up, right? The name of the game today is just simply talking about some of these ways that you could, if you wanted to take this to the next level, how you could start to simulate phenomenon like sun, wind, and light, use that information, generate like literal solar data that I'm going to show you, and then actually start to plug that in to begin to inform, let's say, how far open your tuning components are closed, right? So you can begin to actually inform the geometries based off of the sort of hyper-local information that you can generate with your digital tools. Again, I'm just sort of showing this for informationally. I'm not requiring you to actually incorporate this into process of project 2, just because I know it's taking a lot to sort of do the digital fabrication, laser cutting, putting these things together. I don't want to derail that. Stay on task, right? But I did want to at least show you that these tools are out there, and as well, all the demonstration files that I have, I've made them available to you in case you do want to dig in. Some of you were actually expressed some interest in doing, trying to integrate some of these things in your process. That's fine. The demonstration files are here. If you want to do that, you can. It's not a requirement, right? And I state that, I hope, very, very clearly in this page as well, okay? So again, I want you to just sort of follow along or just sort of look and watch. Right, if you need a laser cut, step out to laser cut or something, I understand. If you have your appointment at 10:30 or something. But otherwise, just pay attention. Okay? Pay attention, watch, learn. This maybe takes like half the class. So then the second half of the class, I can just float around and help out with anybody working and needs a little bit of help here or there as you try to finish up laser cutting, try to finish up assembly, etc. All right? So I have several files here. I'm just going to show what they do. First and foremost, I was just talking about, I said the word Forma. That's a web app that Autodesk, the makers of Revit and AutoCAD, have put out that helps you with some of the pre-design stuff, but also with the analysis stuff. It also is a way to get fairly accurate site information. Have any of you used Forma either for studio or work or anything? Anybody know what I'm talking about with Forma? No? Okay. That's fine. But here's what it looks like, right? You can go to Forma. In fact, we'll be doing this for Project 3. That's how we'll get the topo for our site in Mount Charleston. It's on the south side of Kyle Canyon Road, sort of looking out over the big vista and towards Mary Jane Falls and Cathedral Rocks right next door, etc. And so that topography is something that you can actually get from USGS through Forma, via Forma. This is what it looks like, right? So I can give it a site. In this case, I gave it the parking lot right across the street from us. Here's the School of Architecture. You can see it's just a massing. This is Tropicana. This is Maryland Parkway. Here's that parking lot. And what I can do is, either with Revit or Rhino, I can link up my model, link up Forma and the site information into my CAD platform. Then when I start to model in CAD platform like Revit or Rhino, SketchUp maybe, I don't know, I can't remember what all the sort of array of things that work with Forma. You can then bring it back into Forma and begin to analyze it. So this is me, first of all, getting the site. And then in Rhino, I have I actually install a free Forma plugin. And so I can say, let's load the site data from this Forma project. It wants to make sure I'm logged in so I can find it. And here in a minute, you'll see the massing, the satellite, the streets, the curbs, etc. Let's see what it shows us here. Might take a minute, apparently. It usually works. So this is the way you can sort of go back and forth. No, I don't want to add duplicate geometry. Right, so here's taking that site and all the site information. We get things like where the trees are, where the streets are, where the building massings are. The building massings are kind of, they're pretty mid, they're kind of like just the machine vision reading the outline for the satellite photo and just extruding at a certain height. Based off the shadow depth, so it sort of lacks some of the definition that you might expect from that dormitory over there or dormitory over there, rec center over there or whatever. But it gives you a base, right? In which case, then I can bring my Rhino model in, and then I can sort of tell it which layers and things I actually want to bring back into Forma. Once you're in Forma, it's a pretty robust, actually, system. It's nice to see these tools sort of mature to a point where they just work. And so you have things like sun hours analysis, daylight potential analysis, wind, shadow studies, etc. I'll just show you what some of these things look like. I'll just look at all the analyses I've ran on this, right? So we have something called daylight potential. This basically just sort of measures how much solar radiation is hitting any face of your building or faces of your building. That's just basically a read of if you start to add apertures, windows, fenestration, right? How much daylight potential you could get in, and it's not. I mean, it's pretty intuitive, right? Like I don't think it's kind of trivial at this point. We know that the rooms are going to get blasted with sun. The south side's going to get the most, east and west, and of course probably the north side you start to have shadow and shade. Of course, this is June 21st, so even the north sides get a little bit of sun throughout the day. Let's see. Let me just go back to history analyses. But what's nice is you can start to look at specific dates. This was December 21st, a lower sun in the sky, longer shadows. And so you can start to understand how this is actually performing for, let's say, the winter solstice, the summer solstice, the equinoxes on either swing season, September 21st, March 21st. And start to understand how well or not it's actually shading on an average, a daily average. Right. Of course, that's different than, let's say, June 21st. Let's see here. Or maybe this is September. Yeah, this is September 21st, right? So you can see, again, the sort of sun's coming at more of a 45-degree angle. And as a result, right, you get a lot of shade down here, less shade on these sides and the depth of the site. So you can begin to understand just how well or not you're when you say, I'm trying to create shade, or I'm trying to self-shade, or I'm trying to create a screen, or I have louvers, where I can very quickly start to understand how well they're working, and then begin to adjust accordingly, make things deeper, or adjust the angles, etc. Right? Another great thing is actually, I found for those who care, and you probably will if you take ECS in the springtime, with the passive systems semester. How you sort of look at windrows from like the actual airport weather data, comfort, and then direction. So it gives you the windrows based on our location. You can see, of course, Las Vegas has a lot of north, southwest, some northwest, some northeast. The rest are kind of iffy. They're kind of a real fluke if they come from that direction. And you can start to map, let's say, velocity, and start to understand human comfort a little better. But you can also turn on the streamlines, which I found really great to sort of understand, where you have blocks, where you don't have blocks, and begin to look at the key directions and try to understand, right, where wind's going to affect you or where it's not, right? That's really important in your urban conditions or, our condition here on campus where we have lots of buildings around us. Sometimes you get, have you guys talked about this at all? Probably not, right? So wind is a fluid, right? Like air is kind of a fluid that moves. In fact, this is like basically a digital version of a fluid mapping table. And so sometimes the wind just goes over a building, has to go over a building, and then again you have a sort of negative pressure eddy, right? So you can sort of shield yourself by having a neighbor that's next to you against the prevailing wind. Other times you have two buildings, and the wind can only go around, and so you're starting to force more wind through a entire opening. That's where you get that wind tunnel effect, right? The velocity increases, just like a hose, right? You have water in a hose, and you put your finger over the opening, and only a little bit gets out, but it goes a lot quicker, right? It goes faster, higher pressure. And so you can begin to sort of understand that phenomenon, very fluid phenomenon with these tools, which is nice, right? Before we had Forma doing this, first of all, it would take a lot of computing power locally on your computer to generate computational fluid dynamics simulation, and it felt like you needed a PhD in computational fluid dynamics to understand how to tweak the settings. This just works, and in fact, it runs on their servers, a remote server, somewhere in a server farm. and then just gives you the answer in about an hour or so. So you can just sort of go, I want to see it now, click it. Then you can go do your other things, do homework, go see a movie, eat dinner, whatever it is, come back an hour and a half later, and it's there. It just works, right? And it gives you some pretty decent graphics to go along with it, right? So we can start to see that really northwest winds wouldn't be too big of a deal here. But if I go to the north winds, ooh, I basically, you can see it going under, right? I've basically created we're gonna have some lift. I basically created a wind sail. And I'm gonna really start to talk to my structural engineer. She's gonna tell me, yeah, we really need to anchor this thing. I see that you don't really have any anchors or points where this thing hits the ground. That's where we need to sort of focus our efforts to make sure this thing doesn't move on us or whatever. All right, so I want to show you that. We'll be using that in project 3, going back and forth between Revit and Forma. You can do it between Rhino and Forma. But I just wanted to show you this, right? Like I don't expect you to do this right now because you guys are busy with the laser cutting. But it's there. If you let me know if you do want to try it, I can invite you to the Forma Hub. I'll invite you anyway for project 3. Okay. So that's one way of sort of thinking about this. Forma is a platform for this, where you can begin to run some fairly sophisticated analysis tools, but it works right out of the box in a nice way. It's kind of nice to see the ecosystem of tools sort of mature to where they just work. Right. And of course you can see, let me just show you, when I was just showing you that sneak peek of Project 3, here it is, right? There's the rim route. So this is on Kyle Canyon, and you can see that we have a significant amount of topo. A north view that can be glazed and just look out over the vista. You can see the peak of Mount Charleston. You can see Mary Jane Falls and all that sort of stuff. And to the south, we'll need to figure out how to solve that glass. We'll actually use your shading components from Project 2. We'll bring them into Revit and fit them to your windows. And then we'll also have created a sort of custom family for to use of windows, very small or certain shaped windows for the east and west sides, right? The idea being that a desert building, you know, we can control the sunlight coming from the south. The north we can glaze. The east and west is where we really want to control things because that's where the sun's sort of lower in the sky. We want to minimize glare and things like that. Just do things very specifically. And I have some custom windows that I've made for you guys, custom family. I'll show you how you can modify the types in Revit to do that. They're this sort of knife blade, steel plate, panes, frames, right? So, and then they project outwards, and then you just have a single sheets of glass. So it's beautiful detail, a la like the sort of windows that you see at Red Rock Canyon Visitor Center that Line in Space did, right? Like the sort of very long sort of vista view. All right. So that's Forma, and I wanted to, again, show you guys that, this sort of sneak peek for Project 3 as well. But what happens if we just want to, let's see, analysis example, I'll just bring this up. If we just want to stay in Grasshopper and start to use those tools, there are ways of doing that as well. And in fact, it's not lost on me that sometimes when you generate these values, like let's say energy values, more solar energy, less solar energy, you can actually use those numbers, that data, back into the recipe for your shading component. So you say, well, my shading component can either be really tall and spiky and closed up and provide a lot of shade, or it can be shallow and open and allow a lot more light in. And if you think about then how you can use those solar values to what gets more light or less light, where you need to sort of shade, where you don't necessarily need to shade, then you can actually use those numbers to inform the geometry for each cell. You guys listening? Awesome. All right, so, sorry, I don't like to call people out, but it's hard to hear myself. So this is something similar. I just used basically just a goofy truncated pyramid, and I'll show you the Grasshopper file in just a minute. But you can see that each one is slightly different than the next when it comes to how tall, what the hell? There we go, okay, sorry. How tall and then how open each one is, right? So you can see that it basically creates a gradient. And that's based off of, you know, where you have shade, where you don't have shade, based off of the solar rays that I was measuring from, right? And plus it makes a pretty sweet gradient effect. It looks like, oh wow, like this stuff facing the west is different than the stuff that's facing predominantly north or south or east, right? And I think inherently we want to sort of look at that as designers, as architects, right? I mean, right? We acknowledge that the sun is different when it's in the eastern sky versus when it's up here in the south sky. The north can be different than the south side of the building, etc. So let me just turn that off. And let's just open up some Grasshopper, and I'll show you a couple of ways to sort of think about this. I'm going to open first the sun exposure analysis. I think this is what I just had up baked into Rhino. Yes, in fact I did. And so first of all, I'm just going to turn that preview off. And you can see that what I'm doing is I've defined a set of sun rays, and there's like 1, 2, 3, 4, 5, 6, there's like 9 of them here or something, 10, 8 or 10, I don't know, whatever. So in other words, acknowledging that the sun's a different location, let's say throughout, let's say part of the afternoon. And this isn't necessarily me sort of saying here's the latitude, and here's the dates, and here's the times. It's just me demonstrating this. I just made some layers. Okay? What I can do is I can actually use, in Grasshopper, I can bring those rays in. Those basically, they're just vectors, a direction and a magnitude. And I can break up my surface just like I always do, divide it into subsurfaces or checkers. And I can basically begin to use this exposure tool. It's in the Mesh tab. Let's see, where is it? Utilities. There we go. Exposure and occlusion. So we can see just how much each of those rays are hitting. But we can also sort of measure and see how many of them are being shaded, or what would you say? Let's see. How many are being obstructed, right? So in other words, we can begin to give it sun rays, and then give this thing out in space and see, at what angles, how much energy is actually hitting each of these little checkers, right? Then what I can do is I can take those energy values. There's a big list of them. And average them out so I can start to understand how much average solar radiation is hitting each cell. I can take those minimums, maximums, and I could remap them and place them in here. So now I can say the minimum is going to be red, maximum is going to be blue, or vice versa. And then I can plug each of those in and generate a set of colors. And then I could rebuild the mesh accordingly, right? So I can take that surface, make it into a mesh, right, which breaks it up into its edges, faces, and colors. And then I can rebuild it by introducing the new colors with the same edges and faces, or vertices and faces, or whatever it is. Yeah, vertices, faces, colors, and create something where not only do we have the values, the energy values, but we can see them, right? So this idea that we can quickly generate a diagram and show where the red areas are, where the yellow areas are, where the blue areas are. The most solar radiation, the least solar radiation, and all the sort of nuance in between, right? But once we have those values, we can also, again, remap them to any sort of minimum maximum we want for, let's say, the height or the opening or the UV parameter for each of these shading components, scale or loft or open or close accordingly in order to generate then a set of components that are more open or less open depending on the values, right? In a gradient fashion. So that's sort of serial differentiation, right? Each one's related, right? They have the same recipe, but this one has a little more sugar, this one has a little more vanilla extract, right? This one has a little more shading, this one has a little less shading, right? As it goes across. And again, I just show you this. If you're interested in this, again, it's not required because you guys have a lot on your plates. But if you're interested in this, I'm just opening up this sun exposure analysis.grasshopper file. It's there for you to download, play around with if you like. You have the time to really do this. Okay. If not, I get it. Okay. The performance feedback loop is very similar. I believe it's just labeled a little differently. It's organized a little differently. And I think it goes a little further in laying out and unrolling things. Let's see what it looks like, right? Yeah, so in this case, I've grouped things into clusters with actual like comments and descriptions. So you can see, okay, this is just taking the shell surface and dividing it into smaller quads. That looks really familiar. This is about generating light rays to measure from. Here's how I, let's say, mesh the shell quads and then start to measure the exposure values, solar radiation values. Here's where I start to generate a bunch of unique values from that energy values to create the sort of variables that get plugged in to make things more or less closed. Here's how I map these things to actually create the color diagram, right? The false color map, right? So you can move on and on and on and sort of see how these things work. That's what that one does. Let's, and again, if I start to bake these things in, this is what I get, right? Sort of, there's the model, and I could bring that into Forma and further elaborate, try to see how it works or whatever. From there, then I'm simply running the Rhino script and generating a set of ribs and then trying to prepare for fabrication. All right. If I just turn these off and let's start with this other one. I have one called, I believe, Egg Crate 05. I just wanted to show you this. This is a quick demonstration of a different way, a different method, leveraging computation to help you sort of solve and optimize for performance. This is a case where I'm going to make an assumption, and hopefully this makes sense to you guys. Let's see. Let's open up Grasshopper. Let's close these. Yeah, close that one too. No, don't save, whatever. All right, recent files and Egg Crate 05. All right, so what you'll see is that I'm actually generating basically an egg crate structure. A set of horizontal louvers and sort of vertical fins or baffles, right? So it's sort of a grid that's extruded out. But what I'm doing, or what I need to do, is figure out how to adjust, let's say, the depth and angle of these to sort of maximize the amount of shading for two different sun angle conditions. So I have this one and this one. You can see if I zoom out, I have two sort of coordinates in space sort of projecting light rays, right? So what I can do if I have, let's say, competing constraints, like I can know how to sort of adjust these things to shade for one direction of light. And then if I adjust it to shade for the other direction of light, then suddenly I'm letting more light into the first one, right? So I have competing constraints, right? And so if it's not trivial in how I can sort of optimize this for two different sort of measurements and try to find that sweet spot that sort of optimizes and gives me the best of both worlds, right? I can utilize something called Galapagos, an evolutionary controller, or an evolutionary solver. So here, what I have essentially are the, and again, it's evolutionary, it's basically a metaphor for how you can begin to think about finding the fittest solution, right? What I have is a set of variables for, let's say, depth and angle. Let me just change the depth here so you can see. I can then make these things angle up or down, left or right. I'll just set those back to 0 for now. With a minimum, maximum. Same thing with the horizontals, right? I can think of those as genes, right? So if I have a sort of genotype, phenotype, the graph is the genotype, and every time I bake something out, I have a phenotype if you think about biology and evolution. So if you think about these variables as genes I can randomly populate, and I can look at, after I randomly populate them, I can look at the results, measure its fitness, and then I can use computation to do that thousands of times in a matter of seconds. Right? Then it starts to understand which genes actually are more fit than other genes. It begins to then search again, do a second round of searching based off of what seems to be more optimal and less optimal. Sort of cuts out the less optimal stuff, starts to move towards the most optimal stuff. And over time, over a couple of seconds for us, but over time, lots of generations for it starts to hone in on the most fit solution, right? Based off of the fitness criteria. So over here, I don't know if you've noticed that, but as I start to adjust things, I'm getting a readout of the blue, where I'm casting shadows, and the red, where I'm just letting unabated sunshine, direct sunshine through. And if I tell it and measure the area that's red versus the area that's blue, and I want to minimize the amount of red, right, then that becomes the goal for the evolutionary solver. That begins to determine the fitness criteria. So let me just sort of show you what this looks like. Just sort of, but it's basically like winding up a clock and then letting it go, just like this. But instead of taking thousands or millions of years to find, something that's more optimal in response, it'll sort of break that down into seconds. So here I can say, I have the genome, I have all of those parameters, all those genes plugged in here, and then I'm always measuring the amount of red, and that becomes the sort of fitness criteria. And I can tell it that I want to minimize the amount of red, right? And then I can go to the solvers, and I can say, let's use the evolutionary solver, and then we'll use the annealing solver. So now, right now, it's showing me like every 10 evolutions, or every 10 generations. But it's showing me how it's just sort of randomly populating this thing, and then measuring the fitness of each sort of result, right? Now it's starting to, you can see every so often, it then starts to isolate what's most of it, uses that to repopulate with new information. So it's starting to zero in on a solution that sort of minimizes for both as much as it can. So we're starting to find that sweet spot where we say, well, we're going to have to make some, unless we adjust the parameters more, that we're going to have to make some tough decisions on, we can basically mitigate this ray. This ray, we're going to have a little more problem, right? Makes sense because this one's actually deeper, so that's probably a winter sun. Right, and so after a while, it gives you something that it finds as fit, right? Okay. So again, to leverage computation, this is the kind of stuff you can do, right? It took me a long time to sort of play around, moving things around. Think about if I had, instead of 2 rays, like 14 rays. Let's say I had 2-hour increments on the sun direction in 2-hour increments on June 21st, and December 21st, and then September 21st, right? That'd be a lot of information to sort of negotiate. This uses basically memory and speed, affordances of digital technology computation, to sort of speed up that process, and basically using evolutionary solver to do it. Let's say stop that solver. Let's try it with the simulated annealing solver. It's a different method, different model, but it's going to show us the different things. It's probably going to get similar results, right? It's no surprises here. Right. So again, just showing these things, demonstrating to you more informationally. They're there for you to play around with, experiment with. If you'd like to use them in your process, you can. They're not required because I know there's a lot to do with laser cutting and assembling. But I did want to show you this today. And we're just about done with the demonstration. But on Wednesday, some of you will have your first prototypes, your first draft prototypes. Hopefully as many of you as possible. Right? What I'd like to do is the good, the bad, and the ugly, this first draft, right? Some of them are going to be in pieces, some of them look pretty good. We'll just line them up along these tables in the front. And then we'll come together as a group and talk about it. You'll notice that in addition to sort of bringing them in so I can see tangible results, whether they go together or not, I'm asking you to upload a couple of just quick photos of that first draft. Maybe it's in pieces or whatever. So I encourage you to upload something, even if you're not done yet for Wednesday. And I understand that. But if I just say, like, everybody go next the following week, then everybody will put it off to the following week. So okay? If not, upload something to show me, get that placeholder, and then later on you can comment in more complete things as we go. Okay? But what I'd like to do is to actually have a really productive conversation around what worked and what didn't work. That's how we learn. Right? We prototype, and the very definition of prototype is this sort of iterative exercise of making, learning, going back to the drawing board, and then remaking, learning. It's a sort of iterative cycle, right? Just like you do in Studio. These tools don't give you that big of a shortcut. They simply either allow you to do things faster or to do more things in the same amount of time. Right? So if you think about a doubly curved surface and generating the structure for it, that would take a long time sort of cutting out by hand manually with an X-Acto knife, right? It'd be in the rear. Trust me, I've tried to do that back in the mid-90s. It was not fun. With digital information, computer, digital tools that allows us to do this thing actually quite fast. Right? So, and with precision. So the rest of this time, again, I just wanted to demonstrate these things. They're there if you want to use them, play around with them, break them, learn from them, ask questions about them. But if not, I understand, right? There's a lot to do. Next week, again, you'll start to hopefully finish up if you need to your first draft, if you need to, right? If you didn't have it by Wednesday, try to finish it up for that following Monday. Right? But we'll start talking about another sort of parallel set of steps while you work towards building your final prototype, and that is looking at making some sort of assembly instructions. Like if you bought this thing as part of a kit at a museum store or something, you know how you, like, did anybody do that? Like you go to a museum store and then there's a kit for like dinosaur skeleton. It's like a series of like, two-dimensional parts and balsa wood. You can pop them out and then you notch them together and you make a little like Tyrannosaurus Rex skeleton. That's essentially what we're doing, right? So if you ever go to IKEA or buy Lego or something like that, boy, this is right up your alley. Because you're going to be making the similar sort of set of drawings and instructions for, slot A goes into tab B, and 00 goes in this corner, and 99 goes in that corner, etc. Okay? And we'll talk about that next week. In parallel with you guys starting to prepare, tweak, adjust, and then fabricate and assemble your final prototypes. Okay? All right. So Wednesday, be prepared for a nice discussion around some tangible prototypes. It's going to be fun. And again, some of them will be pretty good, and some of them will be complete disasters. That's the idea, right? That's why we do it more than once, because I understand the first time you try something, it's challenging. And you have to make some assumptions, and you don't necessarily know if they're going to be right or not, right? But you're trying your best. That's all I ask. By the final prototype, they'll be much better. Trust me. I see it every year. All right. So with that, we have the rest of the time. I can float around. This is work time. I understand if you need to go and laser cut something. If you have a time at 10:45, you're like, oh gosh, you're just staring at your watch saying, Josh, I gotta go. Right? Do it. I understand, right? This is the part of the week where it's GSD, get shit done, right? I understand. But I'm here in case you need any individual help. Some of you have been hitting me up with office hours. Perfect. That's time to do it. But we have some extra time now, about 45 minutes or so, 40 minutes. So let's get to work. And I'll be here I'll be the last person here, I guess. Whenever. If you guys need to go, you need to go. But you guys are adults. I think you can manage your own time as efficiently. Hello. Let me move slide this over so you have some room to set your laptop up. I don't want you to drop anything. Is that better?
Yeah.
Look at that bad boy. Oh. Yep.
Wait, let me grab my mouse.
Yeah, totally. 100. And in the meantime, I'm just going to zoom extents to Z. Boom. There we go.
But yeah, I just wanted you to look over it to see if
Outside and
I had
inside. Now, do you have labels for each of these? Yeah, you do.
these
Look at
ones
that.
I do.
Boom. All right.
So, I
That's
would
looking
just
great.
have to have like 3 18 by 32s
Yep.
for my material.
Yep.
But I just wanted you to double check it, see if there's anything I missed.
We have these used. No, looks good. We have the rib, we have the structure, and we have the skin.
Okay. All right, I just got to buy my
Nicely done.
materials then.
Yep.
All right, thank you.
You have a time set up?
Yeah, at 3 o'clock.
Okay, perfect. Hey, hey.
I'm not sure exactly how you have that set up, but I have all mine here.
There you go. All right, I'm going to check a couple things, right? First thing I'm going to check is, do you have the unit set to inches? Just making sure, right?
Yeah.
Humor me. Sometimes I assume that, and then it's like, oh, why is this cutting out really small or really large?
Mm-hmm.
It's because it's set to millimeters or feet instead. So let's just double check that.
Yeah, it's a little funny. Sometimes you have to
Yeah, I hear you. It's in inches, perfect. All right. Yeah. So what you need to do now, if you've baked all these things in, so what you need to do is you need to bake these in on the right layers.
Right.
Okay. But then after that, you make an 18 by 32 frame, offset it in 1/4 of an inch, right? and range everything inside, just like it's a laser cutter bed. You're looking down on the plan.
Right.
Okay.
So as far as that goes, is that on that same device that you used, where you showed me the different like frames?
It's just 18 by 32 boxes you're drawing. Just draw some rectangles that are 18 by 32.
Yeah, 'cause I got the board over there, and I need to carve that out to 18 by 30.
You need to cut it down.
Yeah.
Yeah.
I know it's a little big, yeah.
Yeah, just measure it out, cut it down. Yeah.
And then as far as 18 by 32 here, I'm just like sold. I don't have to put this in any other like cider oven, right? Like I don't.
Polyline. No. Ortho.
Oh, you mean like
Yeah, I'm literally just drawing. I'm just drawing the shape, 18 by 32 on XY plane,
oh.
and then arranging these things inside like it's the laser cutter.
Oh, that's all. So bake it and then do that. Oh, okay. And then on top
That
of
makes a better sense.
yeah, it makes better sense.
Okay.
And is there a way that they can do it without a drive? I have to drive no matter what, right?
You have to be able to give them a 3DM file,
3 and 5.
the Rhino file.
And that's gonna require a drive, right?
If you have a thumb drive that works. If not, then email it to yourself and then open up the email on that computer. I don't know. You might just ask like, hey, I don't have a thumb drive. Like, do you have one I can just transfer it over on?
Okay, yeah.
Or,
I was
you know.
thinking about running to them and doing that anyway, just to see whatever I can do to avoid spending.
But
more
what you
money.
need to do is bake, and then arrange, and then arrange them in that 18 by 32 frames.
Just all right. So, all right, perfect. All right, thank you.